So now we completed the plot. Now we know how to plot for one length, and for a single plot how we know how to plot. Now suppose we want to sweep the length and plot the GM over ID curves for different length. So let us see how we can do that. So as usual, I am first doing the nmos. Our nmos is here, nmos test bench is here. I am loading the state, the previous state as we did in the first tutorial. And now I am doing a parametric analysis. So we saved the state of this also previous. So just load the state. So we sweep the channel length from 180 nanometer to 500 nanometer in linear steps of 80 nano. So this is what we want to. That is what we want. That is characterize the GM over ID for different channel length. So here I am not running it. I am directly saving the Ocean script. So create an Ocean script for parametric analysis. So here I am naming it as param underscore nmos gmid, and I save this. So here is our file. So let us open the file in a good text editor. So this is our param underscore nmos and gm over id. So here it is. You can see the parametric analysis and all the you can just read the Ocean script, and it is very easy to understand. Now the only thing I want to add here is one line, that is our previous line to print the file, to print the data to a file. So we can just copy the same line that we used before, copy that, and just paste it here, paste, save it. So if we run this, it will rewrite the nmos.dat file. So it's okay. We already used the previous file for plotting individual value, and now we will have the nmos file. We will have all the data. So what we are expecting here is, in the first column we will have all the VGS. In the second column we will have ID for a particular channel length. The third column we will have GM corresponding to that channel length, and GDS corresponding to channel length, and up to VTH corresponding to channel length. So after that, all these parameters will repeat for the next channel length. The output what we expect is, first column is the VGS as usual, and then for a particular value, and then for a particular value of channel length, all these parameters in the order. After that, and for all these parameters for another channel length, then all these parameters for next channel length and all. So this sequence is very important because we usually delete the first line of the file to make things easy. So if you are confusing, you have to write it down, the sequence. Now I am running the file. So it was param, yes, param underscore nmos underscore gm over id ocean. So run it. So it will take some time to simulate across all the 5 channel lengths. So first run. It is sweeping VGS and doing the parametric analysis for channel length for 180 nanometer to 500 nanometer with 80 nanometer step in the channel length. So totally we have 5 simulations, that is for 5 different channel lengths. So the simulation is over now. Let us check our file. Output file is nmos.dat. Open it. Now you can see a lot of values here. So first value is the PC, then id, gm, gd, gg, vt, then again id repeats. The id repeats for a different channel length, then gm repeats for different channel length, and gd repeats for different channel length. So as usual, we will delete the first part of the line. We will delete the sweeping of the channel length also, because we know these values. So I'm deleting all the, I'm deleting all the first information. So we want the output to start from this 200 millivolt. So delete. So now I have all just the data, but I know what is the sequence. The first column will be VGS, second is ID for a particular length. Assume, okay, the first channel length it will be the for 180 nanometer. This is the GM for 180 nanometer. This is GDS for 180 nanometer. This is CGD for this is CGG for 180 nanometer, and this is VT for 180 nanometer. So now this will be again ID for next channel length, and this pattern will repeat. So I'm just saving the file, and now we have the nmos. Similarly, we can create that the same file for pmos. So let us close the nmos and open the pmos file. So parametric analysis, here also you can simply load, because we saved the state earlier. It is from 180 nanometer to 500 nano with linear step of 80 nano. Save the question. So now I am naming it as param underscore pmos underscore gmid. Okay. And here it is our file. So as usual, simply copy paste this line and change the nmos to pmos, so that we and simply change the nmos to pmos, so that nmos file is not overwritten. We will get all the data in the pmos.dat. Save the file and run the parametric portion script. So I'm running param underscore pmos underscore gmid.ocn. So it will take some time to run all the VGS sweep for different values of channel length. So total it will be 5 steps. So it will be 5 simulations. Let us wait for the result. Okay, the simulation is done, and let us open the file nmos.dat. So here also we can see all the files, all the information, and as usual, we want only the information that start with 200 millivolt. Rest of the thing I'm deleting to make things easy in Matlab. So just save this, and we are done. So we have the files. We have all the information of the nmos, of pmos, both nmos and pmos in the nmos.dat and pmos.dat. So now we can use them in Matlab. So let us see how we can plot the GM over ID curves for different channel lengths. Let's go to Matlab.
I got the files by sweeping the channel length as a parameter, and I saved the file as nmos and pmos. It's the same name I used, but I changed the location of, now it is gm over id under param. The param stands for the parametric sweep. So let us open the file and see whether it contains the data. Yeah, it you can see it's all a lot of data we have. And for similarly for PMOS we have a lot of data. Okay, and now let us see what are the changes that we have to make our nmos and pmos program to plot the different length. So if we first we start with the nmos. If we run this nmos, okay, before running this nmos I just want to change the location of the files. Now the file location is gm over id underscore parameter, that is param. So copy the location, and I am asking the Matlab to load from a different location, so paste it. So now the location of the file is changed. Similarly for PMOS also I am changing the location. So let us see what are the other changes that we have to make to plot for different length. So now w is same for all the length, so we need not change anything for the w. And the vgs, yeah, vgs is same as now also in the file the first row is first column is vgs, so we need not change anything for the vgs. But id, id is not the second column is id, no doubt in that, but id will be repeating after some column, id will be repeating for a different length. So the format of the file will be first row will be the vgs, first column will be vgs, second column is id, third is gm, fourth is gds, fifth is cgg, and sixth is vth. And the seventh, again the id of the another length will start. So initially it will be the id and gm, gds, everything for length is 180 nanometer, and once that finished it will start the id of the next channel length. So we can simply modify this. So after the 2, make a space and paste it once again. So after the 6, 7 will be again current for a different value of channel length. So after 7, 8 will be gm for another channel length, and so on. So I hope you got the idea. 8 will be, if it is 180 nanometer, it will be 260 nanometer. Now it will be the gm of 260 nanometer. Similarly here it will be 9, and here it will be 10, and here it will be 11. So now we got id, gm, gds, cgg, vth for two channel lengths, but we know we have 5 channels. So similarly we have to fill all the similarly we have to get the channel length, all the data for all the channel length. So after 11 again it will repeating, it will be 12, and it will be 13, it will be 14, 15 again will be cgg, and 16, again will be vth. So now we got the values for 3, that means 3 channel length, and now I am copying 2 at a time so that our editing become faster. So we will give the appropriate name after pasting all of them. So after 16, 17 will be again id, 18, 19, 20, 21, 22, 23, 24, 25 and 26. So this is 1 2 3 4 5. Now we got now we are ready to save all the parameters corresponding to the 5 different length, but our VGS will be same, and it will be VGS is the first row of the file. So but when we are doing the maths which contains the VGS, for example this VGS minus VTH, it doesn't match because VGS we have only one column, but VTH we have many columns. So for the simplicity of the calculation, I am filling the VGS with the same value, so that we need not change any of this expression. All of the expression will be valid if the VGS is also having the same number of columns. So I am just filling the VGS with the same value 5 times, so that all the maths will be easy. So we can, all this expression will be valid then. So let us plot, let's try to plot and see if there is an error. Now let us plot and see is there any error. Yeah, so these are the curve for different channel lengths, and we plotted all of them directly with respect to GMID because we didn't change any of these curves. That's the beauty. We need not change any of these curves, any of these expressions, and but now currently we don't know what value, what length is what. So you can give them that information also by using the command legend. So I am writing this here. For example, you can write legend in the bracket. I am not writing the value of the channel length, instead I am writing L1 that is first channel length, then L2 is the second channel, similarly L3, L4, and now finally L5. So let us see what happens if we give the command like this. There is a mistake, so it is LEG. Oh sorry, I made a mistake here. The legend spelling is LEGEND, my mistake. And let's see what happens now. So in the first curve we got what the colors depend. So we got what is L1. So here it is the minimum channel length, that is the 0.18, and L5 is the 500 nano. So similarly we can indicate this in every graph. So just copy, paste here, paste here, paste here. Now we can see in every graph what the color indicates. So these are the GM over ID graphs for all the GM over ID plot for different channel length, and this is our main objective of all this tutorial. And if you want any other parameters, you can make this, you can make the expression here, and you can edit this plot, and you can play with Matlab. Matlab is a very powerful tool. You can play with it, and you can generate whatever plot we require. So we got all this beautiful plot for the nmos now, and let us generate the same plot for the pmos. So pmos, we can reuse this code what we have for the pmos. We already changed the parameter, the folder where the pmos data is here, and the only difference here is Similarly, what we did for all the nmos values, here we have to do the same for the pmos. So what I'm trying to do is I'm copying all this value, copy, and I replace. So I want to replace all the nmos with pmos, so let us do that. I want to find nmos and replace that with the pmos. So find next, start from here, replace and replace all, close. Now I replaced every nmos with pmos, and I don't have to change any of these codes. All these codes are valid uh, from the previous run. So let us plot our curves, and we got all the curves except we don't know now which length is which color. For that we have to copy once again this legend, copy, and instead of L1, L2, L3 you can really give whatever the channel length you use in your simulation. So it is just an illustration purpose, I give just L1, L2 and L5. So this L1 is represent 180 nanometer, and this L5 is really 500 nanometer. So run the simulation, and this is the final plot for the PMOS. Similarly, if you want, you can plot any parameter by making this first making available in cadence itself. Whatever parameter you want, you can save in the data file, and from the data file you can load them into Matlab, and Matlab is very powerful tool. You can plot whatever you can plot almost anything versus anything in Matlab. So let us see our nmos curves once again, and I think you will be very familiar with all these curves because these are the typical curves that we use for GM over ID technique. And the same graph for the PMOS, it is easy to plot. Once again we plot and we finish this tutorial, and this is the same graph for PMOS. So in some of the method we also need ID by W with respect to GM over ID. So I'm just illustrating that also once again. So instead of FT into GM over ID, I am trying to plot ID by W, so that we have here. So the label also I am changing as ID by W. So let's plot it. So this is the ID by W with respect to GM over ID, but many cases this axis we want in the logarithmic axis. If you see many of the typical plot of ID by W with respect to GM over ID, you can see the axis in logarithmic. So it is not difficult for us also to make in logarithmic. So that is the, so instead of plot, just write here semilog y. Semilog y means y axis will be in semilog y GM ID versus ID by W. So let us run the code, and we can see now this is axis in the ID by W with respect to GM over ID. So by this we covered almost everything with respect to GM over ID curve generation, and we started with the introduction to GM over ID technique, and then we characterized nmos and pmos for particular length. For minimum channel length we characterized nmos and pmos, and then we did the parametric sweep for different length, and in the another tutorial we plotted all these curves in cadence itself using the help of a little bit of ocean scripting, and in this tutorial we plot everything in Matlab also. So in characterization I think this part is over, and we can stop the tutorial now, and thank you for watching.